I thought rather than present you with the latest work that we do, I might give a review of the field of invisibility, metamaterials, transformation optics, and so on. So the professional invisibility men amongst you who can perhaps nod off for a little bit whilst I instruct the rest of you in what's been going on in this field. So in conventional optics, we have this Snell-Descartes law, and it served us well over hundreds of years. And the reason for that is that the law gives us a very physical picture which we can hold in our heads of how light will behave. So if you're designing a piece of kit, you can already see in your mind ahead of time how that piece of apparatus is going to work using this law. Of course, we also have Maxwell's equations, which are exact at the classical level, but they are not intuitive, I would suggest to you. They're very compact, there's a set of differential equations, and it's not clear how if you alter one parameter, Maxwell's equations will change what's going on in the system. And so one of the ideas which we've been pushing is the idea of transformation optics, which is an attempt to capture the simplicity and intuitive nature of Snell's law and at the same time be exact at the level of Maxwell's equations. So there they are, you're very familiar with them, but I would suggest to you that they are not transparent, let's put it like that. By the way, it is this coming year I think the 150th anniversary of Maxwell's equations, and he actually developed those equations not in Cambridge as many people think, but in King's College London, and they're holding a series of celebrations beginning this month and continuing for the whole year with a series of lectures on the ramifications of Maxwell's equations. They were a remarkable set of equations because they were equations which worked for the first time in terms of a field, and that set in motion the whole notion of field theory, which has been such a central element of theoretical physics since that time. They were controversial because they predicted at the time that light consisted of electromagnetic fields propagating through empty space. And of course that generated the controversy of what was this medium through which the waves were propagating, because before that time the fields, if you like it, that existed were not independent entities. They were displacements of a fluid, if there were water waves, for example, and the question was what was being perturbed when these electromagnetic waves were propagating. And eventually people came to the realization that nothing was being perturbed. What was happening was that these fields had a reality of their own, quite independent of the fact that they're in empty space. So very, very profound consequences. Now it turns out that if you write Maxwell's equations in any other coordinate system, that they're still Maxwell's equations. And all that changes are the values of epsilon and mu that you must use in that particular coordinate system for Maxwell's equations to describe electromagnetism there. Here I've talked about the refractive index because this was a popular lecture in the first instance. And that gave us the idea that if you take a field line and you distort the coordinate system, then that field line is attached to these parts of the coordinate frame. And as you distort the coordinate frame, so the field line is also distorted. And so one way of imagining the manipulation of fields is to imagine that the field lines are embedded in some sort of rubber sheet, which is the coordinate system you start in. And then to change where the field lines go, you pull on that rubber sheet, and in doing so, you move the field line. And then when you're done, you look at the formula for the new epsilon and mu in the distorted coordinate system, and if you have a material with those values for epsilon and mu, then the field lines will indeed follow that trajectory. And for obvious reasons, this is called transformation optics. Now, the attraction for me, at any rate, of this way of looking at things is that just as in Snell's law, we can draw these lines which are trajectories of rays, we still have trajectories of lines, but in this case, field lines. And we even can write a generalized Snell's law, because this rule of the field lines being attached to the coordinate system applies to all conserved quantities. So D and B are conserved. The lines have no beginning except on charges, no end except on charges. And also the pointing vector is conserved. Now the pointing vector can be considered as a generalization of the rays which appear in Snell's law. So this, you could derive Snell's law by thinking about it in these terms here. So if you like, we're going to take Descartes' law and generalize it. And here is the formula, which to a mathematician doesn't look very complex, because it just involves the first derivative of the coordinate transformation. And this tells you how epsilon and mu transform from one coordinate frame to the other. And there's this simple formula. But I want to show you that there's, in fact, you can still retain the intuitive view of these things by adopting this approach. I think I have it here somewhere. That seems to vanish from my set of slides. Oh. Sorry, I have that. I beg your pardon, I seem to have deleted that from my slides. Okay, but I can tell you it in words. Let me do the following. That you can derive this other than by mathematical theory of transformations. So if you take the most elementary distortion of space, which is a compression of space, then you compress a region like this, and if you require that the ray which goes through that compressed region arrives with the same phase at the end of the compressed region as it did at the end of the uncompressed region, then you can find out what the values of epsilon and mu are. And had I got the slides with me, I'd have gone through the derivation, but let me tell you the result. So if you squash a medium in this direction, epsilon and mu increase by the inverse of the squashing factor perpendicular to that direction. And along that direction, you decrease epsilon and mu by the compression factor. So it's a very, very simple rule. And by applying that consecutively to the three axes, you can create any shape, any aspect ratio of cell you wish, and by rotating the cell, you can know the orientation of principal axes. So I could crawl over this picture with a ruler and measure how these cells are distorted, and then without going to these formulae here, I could tell you what epsilon and mu to put into this, this system here. So it's very intuitive at every level. And if you ever have to work in a situation where Snell's law can't help you because you're hugely sub-wavelength or whatever, then I would recommend this way of looking at Maxwell's equations to you very strongly. So we have all these tools, and as I said last night, if you want to do anything with them, you've got to find a material. And there's a huge shortage of materials in optics. There are many things we'd like to do but can't because of lack of materials. And so this idea of metamaterials, which has been going for some time now, helps us in many ways. So the idea is to generalize the concept of material properties due to polarization of atoms and molecules, and instead the entities which we polarize are a little bit bigger, but still less than the wavelength, because you want to retain this simplicity of description of a system in terms of the effective epsilon and mu. Now these things are big enough that you can actually manufacture them even at optical wavelengths, so they will be tens of nanometers across in optics. But if you're working at radar wavelengths, which are the order of centimeters, then these structures are even easier to make and are a few millimeters across, and are usually made by etching printed circuit boards. Now at this point, I think it's worthwhile making a contrast between metamaterials and photonic crystals. Both derive their properties from the structure. But the difference is that in photonic materials, you deliberately exploit the phenomenon of refraction. So it has to do with Bragg scattering, band gaps, and all that sort of thing. So photonic crystals have to have their lattice spacing at the same order of the wavelength, because that's the way they function. Metamaterials are different. They should always be described by epsilon and mu, otherwise they're not much use as a metamaterial. And the individual elements are usually in a periodic array, but don't have to be, and they are much smaller than the wavelength, because if they weren't, you couldn't use epsilon and mu. Now, that's a very important distinction, because in many ways, photonic crystals are much more subtle than metamaterials, but the subtlety they contain leads to a huge problem in design. So suppose you wanted to steer a ray of light around a photonic crystal. You could do that, but you'd have to solve the whole problem at once. So you'd have to ask the computer, what lattice spacing should I have here? What lattice spacing should I have there? It would be an absolutely enormous calculation, and by trial and error, you'd have to arrive at the right system. So the advantage of metamaterials is it splits the problem into two. So using transformation optics, if we want the rays to go in a certain direction, then transformation optics will tell us very, very simply, almost without computation, or at least with trivial computation, what values of epsilon and mu you must have. It doesn't care how you get them. And then metamaterials, because it works in terms of epsilon and mu, because there is this simple summary of how a metamaterial functions, your next task is to design epsilon and mu, and that's a local problem. You don't have to worry about what's going on over here, because that's been addressed with transformation optics. So by splitting the problem into two easy bits, you've made the whole design procedure much easier, and engineers will thank you for that. So I'll just show you a few metamaterial structures. Many of you will be familiar with these. This is the first metamaterial, well, it's not the first metamaterial, it's the first magnetic metamaterial that we were involved in. I was consulting with Marconi at that time, and Mike Wiltshire was an employee of Marconi. Marconi of fond memory, now crashed in the dot-com boom. They're no more. Here is his first metamaterial. So the dimensions here about 5 millimeters. This is a printed circuit board. This whole thing was designed on a computer. Then you sent the computer, the CAD file, over to printed circuit board manufacturer, and they etch these rings, and back in the post comes your metamaterial. And I have to say that if you want to introduce a new technology, and hitching a ride on an old technology is a very useful thing to do, because you don't have to invent everything as you go along. And in fact, nearly all the early metamaterial structures were based on this idea of etching on a printed circuit board, because it's just so darned easy to make fairly complex structures. This is the infamous split ring structure, in which you take a ring and you break it so the current can't flow right round the ring. If you put a magnetic field normal to this ring, it will induce a current, but that current can only flow because you're charging the capacitance between the ends of these prongs here. And so you have an inductance because it's flowing in a circuit, a circular path, and a capacitance, inductor capacitor resonator. And this thing resonates at about 10 gigahertz. It has an enormous positive mu just below 10 gigahertz, and above 10 gigahertz it has a negative mu, which is a property which triggered the renewed interest in negative refraction at David Smith's laboratory in San Diego. So that was a huge catalyst for the growth of metamaterials, and I first publicized that design in 1999 at the Laguna Beach conference, and the whole thing took off from there. This is David Smith's take on metamaterials. Here's our split ring, and what David did was to combine two structures that we've been working on. One was the split ring, which gives you negative magnetism, and the other was this thin wire structure. You see this wire here? That's actually on the other side of the circuit board. And that gives you negative epsilon. And the two together, if this is satisfied, gives you a negative refractive index. And this is the first structure ever to show a negative refractive index. You don't see that in nature. You need metamaterials to do that. And that was done, I think, in about, I haven't given the reference here, I'm sorry, but I think that was about the year 2000 in David's lab, and created a fuss at the APS meeting that year. A structure I love very much, but is not beloved of research students, is the Swiss roll structure. And the reason is that unlike the split ring structure, each one of these little microstructures is lovingly rolled by hand by a research student. So if you want hundreds and hundreds of these, as you do, then it takes quite a while to do that. And this really hasn't caught on, but I'll tell you about it anyway because I love it so much. So what happened was that we were funded by the military to make these split rings because they're interested in radar. Radar works at a few gigahertz. So this is a small sparse structure with a resonant frequency in the gigahertz region. It's designed for that. Now, the Swiss roll structure consists of, again, a printed circuit board, but a very thin and flexible one. So you just roll it round a dowel, about like that, and the printed circuit board is conducting on one side and then an insulator on the other. So now if you put a magnetic field around here, the current flows round and round and round, but there is no continuous circuit unless you include the capacitance between the inner winding and the outer winding. Now you can see there's a lot more capacitance there, there's a lot more inductance there, and the reason for that was that the funding switched over from the military to the medical, and the money came from the MRI arm of the company. And this works at 21 megahertz, which in an old-fashioned MRI setup is the frequency at which the RF comes. So this was designed to help control the RF magnetic fields in an MRI experiment. And the reason I love it so much is that the diameter of these rows is about 1 centimeter for 21 megahertz. The wavelength at 21 megahertz is about 10 meters. So this is almost as good as glass. The ratio of the microstructures to the wavelength is 1,000. And that's about what it is in glass at optical frequencies. So that was nice, but it's not been a popular structure. It has a reincarnation in work which my colleague Richard Sims does on MRI. He is designing a magnetic wire, and these are a bit like magnetic wires, you see, because once flux is, if you're on resonance, once flux is captured inside this tube, the only place it can go is to come out the other end here. So these are magnetic wires. And the challenge was to make them flexible. And Richard has done that. So you can now deliver and collect magnetic RF signals in MRI using a magnetic wire rather than a metal wire. And that's a much safer thing to do for various reasons I won't go into. Okay. So the challenge was on to do this negative refraction thing at optical frequencies, because David Smith had demonstrated a material with negative refraction at RF frequencies, but what people really wanted was a visible a version in the visible region of the spectrum. So just to remind you, if the refractive index is positive, then the light comes this side of the normal, and if the refractive index is negative, then this angle goes the other way, and from Snell's law, or Descartes' law, you get a negative refractive index. And I always find it surprising that such a small twitch of an angle should have such profound consequences, but I can perhaps indicate to you why that might be and why it caused such huge controversy at the time when David's paper was published. And just think about this a little bit. So this is a translationally invariant surface. So the parallel component of the wave vector must be conserved. Okay, so it's clear what the wave vector is in vacuum, and it's clear that the projection onto the surface goes from left to right. Now, if we made the same interpretation inside this negatively refracting medium, then we would say that if the beam comes out this side, you have no choice, but the projection of this vector onto the surface is in the opposite direction. So it violates this very, very fundamental law from group theory, not from physics, that parallel wave vector is conserved. So how do you wriggle out of that? And the answer is that this vector here is in fact the vector of the group velocity. It is not the wave vector. Now, in vacuum, we confuse the two because the wave vector is always possible parallel to the group velocity. But in a negative refracting medium, this cannot be so because you violate this conservation law. And in fact, what turns out is that there are actually two choices in an isotropic medium for the relationship between the wave vector and the group velocity. Compatible with isotropy, there are only two solutions. One is parallel to, and the other is anti-parallel to. So if you say that in this medium, the wave vector has to be anti-parallel to the group velocity, then you can satisfy this law. And if that's not true, then you can't have negative refraction. So this is a very curious medium because it's one in which the waves go one way and the groups go another way. Very curious situation. So you immediately see, just from this diagram here, without doing any real maths, that this is a very strange material. And the metamaterials that have been deployed to get this effect at optical frequencies, of course, it's a much more difficult operation than for RF because the dimensions have to be much smaller because the wavelength is now very small. So this is 1 micron here. This is the so-called fishnet structure. This example made by the Jang group in Berkeley. It consists of a sandwich-like structure, alternating layers of 30 millimeters of silver and 50 millimeters of an insulator dielectric magnesium fluoride. And this structure will show a negative refraction effect, it turns out. So progress is being made. So to my mind, of the various phenomena which appear in metamaterials and transformation optics and so on, the most striking is negative refraction. But I think you can see from this structure that it's very difficult to implement negative refraction. So when the next big thing came along, which was cloaking, people deserted negative refraction in hordes because you could have easy pickings with a cloak, which is easy to design, and also access to the press, which is very good for people's ego. So on to invisibility, and this is an old story by now, 2006, the first papers published nearly 10 years ago. And the challenge in invisibility is more than just making something black. That's conventional stealth, and it works in a radar dark environment where all you have is a beam going outwards, and if it hits something black, you don't see anything. And if you take the beam away, then that thing isn't visible anyway because it's not scattering any light. But if you're in a radar bright environment, or certainly at optical frequencies, then of course, even though I'm not shining a laser beam on Peter, you do see him because of all the reflected light. In fact, that's the main channel through which we observe things, reflected light. And so what we have to do is, yes, Peter should be black, so my laser beam doesn't reflect from him, but also you have to eliminate the shadow. And it's that elimination of the shadow which is the greater challenge, of course. And then, of course, you have true invisibility. Now, this challenge in invisibility came to the fore because if you'd done the way around things happened was that we had transformation optics, and then we were looking around for things to do with it. But if you started with the challenge of invisibility and wanted to invent a tool which solved the problem, then you'd invent transformation optics. Because what you want to do is to take a region here and steer light away from it, but in such a way that you only divert the trajectory of light inside a cloaking region, which I've indicated by this square here. So you're allowed to perturb the light inside here, but outside here the light mustn't move. But remember that rays, fields, whatever, they only move if you move the coordinates. If you don't move the coordinates, they don't move. So that's perfect. So you only mess about with a rubber sheet inside here. You make a little hole in it. You tear a bigger hole. You compress the rubber inside your cloak. So that becomes a cloaking region. And then you ask, from the compression you've had to do, what is epsilon and mu? You stick those in. The ray trajectories are diverted inside here, and they don't move outside. So it's the neatest possible solution to designing a cloak. Really very satisfying. So as you can imagine, all you have to do is to take the stuff inside that was inside this circle here and stuff it into this region here. It doesn't matter how you arrange it there, it will still be a cloak. So there are many, many different cloaks you can devise according to how you stack that rubber sheet inside this cloaking region here. And the very simplest one, which we chose in our paper in 2006, was just a, excuse me, a linear compression along the radius. And this very simple mathematical formula will give you the values of epsilon and mu. there are other choices, but in this case, there's always a singularity on this inner surface here, whatever choice you make, because you're taking something from a point to a circle, and that creates a singularity. And that's not a difficulty at RF, because you can have infinite, almost infinite conductors through very good metals. So that was the first cloaking design. And this iconic diagram, which is drawn by Dave Schurig using Mathematica. Actually, when the paper was published, I got a call from Mathematica and said, "Do you have a Mathematica license?" I said, "No." He said, "Do you realize you..." But of course, Duke University did, so we're okay. So that's what the cloak is doing, and this has been shown many times, so I won't dwell on that. So what happens, in fact, is that you, just like you see a mirage here, what the cloak has is a graded refractive index, and it's bending the light, which is something you don't normally see, but you do actually see in a mirage, desert mirage, and here are road mirages, which we see in Europe. Here's a picture of the first cloak built for RF with metamaterials. This, so you can see the split ring design survives in the cloak, and the structure can easily be changed from the inner piece of metamaterial to the outer, and that gives you a gradient in the a refractive index. Actually, this is mu, which is having a gradient here between the inner and the outer bit, and that fulfills the parameters for a cloak. Actually, I did mention that there are many ways that you can compress the rubber sheet into this cloaking region here. In fact, in addition to that, you have several choices of the topology of cloak to build. So you can build a cloak in which is basically spherical in topology by starting from a point and ripping out a sphere. Or you could say, well, I'm going to have a cylindrical cloak, and then you start from a line and expand a line into a cylindrical hole. And the third way, of course, is just to start with a sheet and expand that sheet. And each of these cloaks, actually, as you go from 3, 2 to 1D, gets easier to build. And the last one is easiest to build. The only problem is that if you start from a point and make something look like a point is invisible. But if you start from a sheet is only invisible if you look at it edge on. Except that there is a trick you can make, and that is if you put a sheet, which it turns out, if you look what the sheet has to be like, it's a mirror. If you put a mirror on top of another mirror, then it's invisible. And there are many instances in radar where you have what's called the ground plane, where the Earth is effectively conducting at that frequency and acts like a mirror. And then if you can flatten, make an object appear to be flat on the surface, then you've effectively hidden it. And so this is called the carpet cloak, hiding something under the carpet. And it was developed by Jensen Lee, who was my postdoc in the late 2000s. And what he's doing here is to take a coordinate system which was square, take a square region here for the cloak, and then what he's going to do is to create a cavity here by, so this is a mirror, and he's going to lift up the mirror so that you have a reflecting surface here and a little tunnel. But because he compresses the coordinate system here, if you ask what epsilon and mu are in this region here, then this will create a cloak which will effectively flatten that little tunnel so that it appears like a flat surface. So obviously if you didn't cloak this, there will be a flash, two flashes from the two facets of this tunnel, whereas with a cloak you just continue to see the one flash. And here I think I have a computer simulation of that. Yeah, so here's an uncloaked tunnel, reflections of the two facets, so it's clear that there's something there. If you look at it with radar waves or with light, if it's an optical tunnel. And here you put the cloak in place, and there are various sorts of cloak you can devise actually. This, both have been realized. So this particular cloak, I said there was a choice of how you stuff the material into the cloaking region, and here what Jensen has done is to devise a quasi-conformal cloak, and all that means is that if you start off with a little square, then after you compress that region, you try to arrange things so that it's as square as possible after the compression. Can't do it perfectly, but you can do it pretty well. On the other hand, no attempt here has been made to keep the little squares square, and all that's been done here is that each column is vertically compressed equally. So each little square has been squashed in the vertical direction here by the same percentage. Okay? And it turns out if you do that right, you can make this cloak out of a homogeneous but anisotropic material, because you've given the same compression to each of these columns here. And I'll show you an example of the quasi-conformal cloak. So you've seen that. So this was made in Berkeley. So what we've got here is a waveguide in a silicon slab. Here's a mirror which has a tunnel built into it. So this is a cloaked area. Here's the cloak embedded in a lower refractive index medium. And the way, this is the simplest possible metamaterial, you change the refractive index by drilling holes in it. The only catch is that this is very, very tiny, a few microns across, and so the holes you drill have to be done with a focused iron beam, a very expensive and delicate instrument. So here's an electron micrograph of the finished article. So here's the silicon waveguide. Here are the holes drilled, and you can see that the density of the holes varies as you approach the cloaked bump here, and that's 1 micron. So it ain't Harry Potter by any means. Now, I always forget which is the experiment and which is the theory here. It didn't matter because they both look the same. So here's a flat surface, a single reflected beam. Same in experiment and theory, as you'd expect. Now you put an uncloaked bump there, and because of the facets on the bump, you don't get a single reflection when the beam hits the cloak. In this instance, you get 3 reflections, and that's simulation and experiment again. But you put the cloak in place, but you've still got the bump under the cloak, and once again, you come back to what looks like a flat mirror, even though you're hiding something in that tunnel. So that was the first demonstration of a quasi-optical cloak. Silicon, of course, is not transparent in the visible region, but it's transparent in the telecoms region. And since this cloaking idea has been, this carpet cloak has been, I don't have the figures to show you, sorry, I don't have the figures to show you, but this version of the cloak has been realized because if you get this angle right here, then you can make the cloak out of calcite, which is bianisotropic and but homogeneous. So the calcite cloak can be much bigger. You can get whacking great pieces of calcite, a few tens of centimeters across, and there were 2 versions of that cloak, one made in Singapore and the other made by Zhang in Birmingham in the UK. I think they both source their calcite from somewhere in China. Most materials come from China these days, don't they? So what next? Okay, so that was cloaking, but in a way, although cloaking is an elegant demonstrator of the power of transformation optics, of how we can very simply design a cloak, you could, by trial and error, also have designed a cloak by using essentially Snell's law. But the power of transformation optics is that it applies to the whole of scenarios described by Maxwell's equations. So, if transformation optics is right, this cloaking theory should apply not just to rays of light being diverted around an object, but also to magnetic field lines. So it was with this in mind that Ben Wood and I set about designing a cloak not for rays, but for magnetic field lines. So here's a magnetic monopole, radiating field lines, and now exactly the same process should happen to field lines as happens to rays if you follow that prescription for a cloak, because it's a cloak not just for rays, it's a cloak for everything electromagnetic. But how do you do it? So I would remind you that I gave this very simple idea of how you can derive the cloaking parameters. So what I want to do is to take the region in that the rubber, in that central region of the cloaked region, and can compress it into the cloak. So if I'm squashing it this way, the rules say that perpendicular to the direction of squashing, the epsilon and mu must increase. Actually, we're only interested in mu in this situation because we're trying to cloak static magnetic fields. So there's no electric field, so we don't care about cloaking that. So you must increase mu parallel to the angular direction. That's easy. We have ferrites, large values of mu. Fine. But it also says that along the direction of compression, you must reduce mu. You must have a diamagnetic material. Now, diamagnetism is an issue. A strong diamagnetic material in nature would have mu of 0.95. Here, we're asking for mu's of 0.5 or something like that. Huge diamagnetism. Once again, when we turn to nature and say, where are the diamagnets with these very large values, or small values, I should say, of diamagnetism, it ain't there. So you have to do it with a metamaterial. And the design we chose was to use superconducting plates. Now, superconductors themselves are not diamagnets, contrary to what rubbish you read in some electromagnetic textbooks. They are merely very good conductors. But you can make diamagnets out of them because their electrical properties mean that they actually expel magnetic fields. So a magnetic field cannot penetrate any considerable depth into a superconductor. So here's a structure with superconducting plates. And if you apply a magnetic field in this direction, if the plates are thin, essentially there's very little perturbation of the field. So mu is about 1 in this direction. And if you put some ferromagnets in here, it would be raised essentially to the value of mu in your ferromagnetic material. Fine. So we've got the parallel to the angular direction sorted. But now what about the diamagnetic bit? So if you put a field line, a set of field lines coming in here, to get through this structure, they've all got to squeeze through these tiny gaps here. And this act of compressing the fields means that you've actually reduced mu. Okay. So because you're squashing the field lines, that creates energy. So field lines do not like to be in this material, and that's the signature of a diamagnet. It tends to expel magnetic lines of force. So this is a diamagnetic system. And you can get extreme values here. So this is a system in which you have 9 layers of those plates, and what's given here in some units, I forget the units actually, is what's important here is the ratio of the length of the side of the plate to the spacing in between here. And that's what's going to give you the diamagnetism. So here you have in some units a length of plate of 133 and a plate spacing of 34. And that already will give you a mu of 0.64. And by reducing this ratio, you can actually theoretically push this all the way down to 0. Now, it so happens that our experimentalists have magnets and superconductors and things, and they offered to measure these things for us and see if this really did make a metamaterial with these properties. And what they did was to take a microscope slide and evaporate lead onto it. Now, lead's a superconductor. And they made the pattern by just scribing the lead with a knife to make these gaps. Obviously there's some error in that, but nevertheless, when they make these structures, you can see that the measured permeability is in pretty good agreement with the theoretical predictions. So we have got a metamaterial diamagnet there, and this was Ben Wood's design for the cloak. So the grey bits are the superconducting sheets with the spaces in between them, and this changes according to the radius. And between them you have ferromagnetic layers. And at that point our experimentalists gave up, and they said, well, we're not interested in building a cloak. And this was about 2006, 2007, I think, something like that, soon after the original cloak. And there the matter lay for some years. And then a couple of years ago, some guys at Harvard, they didn't even tell me they were doing this, so I discovered it by accident. These guys actually made this cloak, and they followed Ben's design procedures pretty accurately. So here are the lead sheets with the gaps between the squares, and they didn't use ferrites as we suggested. They used this permalloy between the sheets here, and that made a cloak with a requisite properties of anisotropy. And then they tested the cloak, and the way they did that was to generate a magnetic field from these two solenoids here and put the cloak in the form of a cylinder here. And what the cloak should do is to exclude the magnetic field from this central region here, so any magnetometer placed here has a 0 reading, and however not perturb the magnetic field outside. And they were very careful to make the distinction between a cloak and a screen. So if all you want to do is to exclude the magnetic field from here, there are much simpler ways of doing it. There are in fact two basic ways. One is to take a material with a very high mu, which is a mu metal, and just wrap it around the object, and that will grab all the fields and prevent them from entering here, but it will create a whacking great dipole moment, so the fields outside will be perturbed and there'll be a large force on that dipole. The other way is to take a superconductor and wrap that around, and the superconductor will also exclude the fields from here. It will actually create a dipole moment of the opposite sign to the mu metal, and that will also create a disturbance of the field here and experience a force depending on the strength of this field. So by judiciously mixing the two in a subtle sort of cloak way, you can make a cloak that doesn't do this. And I'll show you those data. Now, I hope I've got the other data. No, I don't, sorry. I've just got the one set of data. For some reason best known to myself, I've deleted a lot of the slides I thought I was going to show to you. Okay, so they actually did the experiments for the pure superconductor and the pure mu metal, and as predicted, they show a great big dipole moment. But here are their data of the cloak, and they have many sensors, but I'll just show you the data from two of them. So this is data from sensor 1, which is inside the cloak, and this is the data from sensor 2, which is just outside the cloak here. And the magnetic field is shown as a function of the current here. So here are the data with no cloak, and of course the field just ramps up uniformly, but if you put the cloak in place, it does its job pretty well. There's no field inside here. But if you look at sensor 2, then of course if there's no cloak there, you get just the red dots which you saw over here, a uniform increasing field. But if you put the cloak there, nothing happens out here. So the field is exactly the same as it was before the cloak was there. So it really does do a very good job here. There must be very skilled experimentalists. I can't believe myself ever making something as subtle and nice as that experimentally. So that was nice because this was the first cloak that actually cloaked fields rather than rays. Obviously, you could not have designed this cloak using ray optics because there aren't any rays there. This is a DC field. So I was very satisfied to see that experiment done as a rather nice confirmation of transformation optics doing a job that nothing else could do. But closest to my heart is negative refraction because it is such fun, actually. It just contradicts so many half-truths that you believed. And I suppose the fun thing you show when you're talking to school kids is, I've used this slide many times with school children, is this, that if you had a swimming pool or a pool of any sort with something in it, a fish or a child or whatever, and you suddenly magically transform that material to have a negative refractive index, when you looked at the pool, you wouldn't see the fish inside the pool, you'd see the fish apparently swimming in thin air above the pool. And so that's one of many lovely paradoxes you get. But let me show you one or two others. Actually, Anantha is here today, and he will remember very well. Where are you, Anantha? Okay, he will remember very well this problem we worked on together, which is to take negative refraction, and you see this negative refraction effect here is actually making a lens, because if you apply the laws of negative refraction, these rays are bent back towards the axis and refocused outside here in the vacuum, and that's why you see the fish above the water. But this lens that you make is planar, and therefore it doesn't magnify, but you can use transformation optics to distort the shape of this lens, so you can bend the flat lens round into a cylinder or a sphere or what have you, and that, as you bend, this bit you magnify and this bit you demagnify, so the bit inside everything inside this cylinder has come from something which has been squashed in there, and everything outside the cylinder is something which has been stretched. So what this device does, here are the values, the precise values of negative epsilon you must have in here, in this formula, and what it does is to take the contents of this green sphere and to, actually it's a cylinder in this case, this green cylinder, and expand them so that viewed from outside, the contents of the green cylinder appear much larger inside this red circle here. And I point out to you, this red circle is a circle drawn in vacuum. It's larger than the lens which is creating that magnified image. Now that's a little paradoxical. Maybe the paradox isn't apparent at first, but I like to present it like this, that if you take, yes, a bottle. This isn't ideal because the plastic is very thin, but if you took a glass bottle, even a very thick glass bottle, with some fluid in it, it would appear that the fluid went right to the edge of the bottle. You looked at a milk bottle, right? You see milk right to the very edge of your field of vision. The reason is very obvious. Any ray that strikes a milk bottle must enter the milk, and therefore it reaches your eye looking like milk. Fine, we understand that very well. Snell's law tells us why it is so. But now imagine that you replace the glass with this negatively refracting lens. Now what Snell's law doesn't tell us, but what transformation optics tells us, is that the milk is now out here. Okay, so you put milk in this central region, and what you see is milk filling this red circle here, and this is all vacuum. Okay, so it's like a super milk bottle. Imagine how that happens. Just to drive home the paradox, I love this. Okay, so here are the rays which are going off to your eye, somewhere over here. And the middle ones are no problem, because this one goes right through. This one does a fancy dance of negative refraction and enters the inner region here. Fine, 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 fine. But transformation optics says, aha, but you're not done with this last ray here, actually to strike the lens. What transformation optics says is that the lens will also capture these rays and pop them into the top half here. So I've drawn in red these rays which are predicted to be captured and are not. So here's a Maxwell equation solver, and it's not done in terms of rays, it's done in terms of waves. So here are the waves hitting the system, and the waves are grabbed by this region here, and they're compressed into this inner region here. I may have an animation of that if I've done my job right. Okay, sorry. But anyway, you get the picture that this is what Snell says, that these rays can't possibly reach here. This is what Maxwell says, and of course Maxwell's got to be right. This region is filled. How can that happen? Well, let's start at the other end of the problem. If we suppose the rays have got into this region here somehow, then their trajectory would in fact go around this loop here, because you have negative refraction here, negative refraction here, and they just circle round that loop. They are in fact resonant states of the system. So when you switched on this field, which is coming in from the left, let's say, what you would first see is that these rays which actually hit the structure would almost immediately fill this central region here. And you would see nothing in this region here. And Mr. Snell would say, aha, I was right after all. But if you wait a little time, the ray picture, of course, is inaccurate, and the rays are not infinitely thin lines. They have little Gaussian tails on them. And these Gaussian tails will tickle the resonances in this region here, and eventually energy will be drawn into these resonances, and they will fill up. But it will take time, because they're very narrow resonances, and the bigger the structure, the narrower the resonances. So that's the way this top half of the milk bottle gets its color. It's through resonant interaction. And there are many sort of paradoxes like this that you can find with negative refraction. And for me, that's the beauty of it, that everything, or not everything, but many things you thought you knew about optics really aren't so. Well, you can have fun and games with that. And one of my other postdocs, Wei-Shung Wei, looked at this. I think I know what's happened here. Yeah. Had this idea. So many of the devices in optics only work if they're very big. And one of the simplest devices is the shadow. So we're all familiar with shadows. You know, you take a black object or object of any color, and if light shines on it, it produces a shadow. But as you know, that shadow is not sharp, even if the light source is a point. The shadow is not sharp, because if that object is small, there'll be diffraction effects, and the light will diffract around the edge. And if that object is of the order of the wavelength, the light will diffract around the edge and fill in that putative shadow within one diameter of the shading object. And so the way around that Wei Sheng proposed was to take a very small object and surround it by a very small lens, which magnified it so that you made an image of a black object, which was bigger than either the cloak or the object itself, and big enough to make a shadow. And here's a COMSOL simulation of waves incident on this structure from the left. Everything outside the outer blue circle is free space. Inside here, he's got a black object, and what should appear here is a black object out in free space, the image of a black object. And if that's a true image, you should see a shadow, which is the diameter of this guy, rather than the diameter of this guy here. And that's exactly what you see. And there are other instances you can quote of that happening. Another example is the corner cube. So if you make, if you have two mirrors at right angles like this, and a ray hits one mirror, it's reflected into the other mirror and goes back along the direction that the first one came in. Some of the moon missions actually put a corner cube on the moon, and it's the way you get laser light back from the moon. If you just send a laser light to the moon, it makes a fairly big spot, and is reflected off in all directions. So you put it on a corner cube, that beam comes back to you, and it's strong enough to be seen, and that's the way they measure the distance to the moon. But corner cubes only work in the ray approximation, so if you want to make a real small corner cube, you've got to put it inside one of these lenses here. Okay, well, that's probably enough. Just want to point out that metamaterials is a growing field. There are a few hiccups along the way, but it continues its onward march. This is 2013, halfway through, so we're pretty sure to climb up to the full citations at the end of the year. And this is the year zero, 1999, when I gave my Laguna Beach lecture. And David Smith was in the attendance, and the field has grown from that point. So the next step, I think, is that this is well established in academia. It's such a fun thing that people really enjoy working on it. But as well as fun, of course, it's got to be important, because if all you have is fun, then that's not enough in my view. And you've got to have products. And here's one of the products which is about to hit the market. It's comes out of an outfit called Intellectual Ventures in Seattle, which is a patent gathering operation, but they also have spin-outs. And one of the spin-outs is a company called Chi-Meta. And they make SATCOMs receivers, and they're made out of metamaterials. So an ordinary SATCOMs receiver has a satellite dish. It's about 30 centimeters across. It's heavy. It's expensive. It's got to be steerable, of course, because you've got to follow the satellite. It takes quite a bit of power. Tens of thousands of dollars. There's a more fancy version of that based on phased array. And for those of you who don't know your radar, phased array is when you take a flat sheet, like something like that, and you have lots of dipole antenna in that sheet, but the phase with which you feed each dipole is regulated by a complex array of transistors. So lots of silicon, hundreds of thousands of dollars, but it's stationary and it steers the beam electronically rather than mechanically. Now it turns out that actually by altering the phase of metamaterial elements through a simple DC current and not through silicon, you can make a very, very cheap phased array. It's really quite easy to make, but subtle to design, of course. And the guys at Chi-Meta, using these concepts of transformation optics and metamaterials, have made a phased array from metamaterials which is steerable through DC currents in this sheet, and it can point at any point of the sky. That's what it looks like. The company is now capitalized to $50 million, I think. Half of it's from Bill Gates, interestingly enough. He's interested in this, I think, because he believes that SATCOMs can be important in Africa, where in some parts of Africa the cell phone network is not well developed and you need cheap SATCOMs. So this should market for about $1,000. It plugs into the USB port of your laptop. What else? I don't have any other slides of applications, but, or do I? Yeah, so, okay, here's another one. This is an application in which you make a lens. So, you know, we've been talking about all these airy-fairy things with super resolution and whatnot, but you can see that the first applications of a technology are usually making something that you make already, but doing it better and cheaper. So it was with the laser. Does anybody know what the first really important commercial application of the laser was? You do. You've heard my talk. Okay, Ross, what was it?
Barcode scanner.
Right, barcodes in superstores, right? And then the laser went on to do what? Eye surgery, welding, and all the other stuff. Well, this is Metamaterials in its first incarnation in commercial products. This is a lens. But instead of making the lens by curving the surface of a solid dielectric, you actually take a thin layer of metamaterials and you grade the properties of the metamaterial so that the index is higher in the center than the edge. And this thing is about 30 centimeters across. It has to be to focus radar waves. It was made for Boeing. And it's about 2 million meters in diameter, and it just weighs a few grams. Whereas the polystyrene version, which is the usual way they do this, comes in at several kilograms. So, you know, these are also being made for Lexus, Toyota, to do the collision avoidance radar in the front of the Lexus high-end cars. I mentioned already that Richard Sims is doing the MRI thing, using metamaterials to make magnetic wires, and he's about to form a company that does that. So I think, oh yes, there's Richard's stuff. I think, as I said last night, that Metamaterials has been a great ride for many of us. It's a radical new concept, and it's always fun to be associated with that. And it really is fun, but at the same time, it touches on quite a bit of profound physics. I think if you could rewrite Snell's law, which has stood the test of time over hundreds of years, and produce a law which generalizes that to Maxwell, I think that's quite an achievement. But also, importantly, it's going on to be commercially important, and that won't be so visible as cloaks and perfect lenses, but ultimately it'll be the bread off which the subject feeds in the future. So thanks very much for your attention. I'm very happy to take questions if you have any.
Who wants to start with the questions? Ross?
Could you describe that stuff that Capasso was doing on those metamaterial-like structures scattered over a surface?
Yeah.
Would you call that a metamaterial application or not?
Oh, yeah, it's very controversial. So let me explain this. Federico Capasso has been making these metamaterial surfaces with elements that look a little bit like what I'm showing you. They're not exactly like that. And he makes a periodic array of these elements, but within each period, he gives some special structure to the arrangement of the metamaterial. So the elements themselves are sub-wavelength, but are on a longer period. So it's a grating. He doesn't like to call it a grating, but it is. And what the structure inside the period gives you is what in X-ray they call the form factor. And which in optics you call a blazed grating. So a blazed grating is when the light when you light it from one particular direction, and then the grating is very bright in that direction, because essentially it's a set of little mirrors. And what Federico has done has fiddled about with the form factor of a grating. It does a great job, but for my, it does what Federico says it does, but he describes it in very highfalutin language, when Blaze grating would do quite well.
It would do me.
Yeah, okay, good.
Any more question?
Too early in the morning.
Okay, I've
Okay.
got one question. John, what is your last invention? The very last one.
My latest one that I didn't talk about, you mean?
Yes.
Yes. Well, what we're doing now is, I really like this perfect lens, but it's very, 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 very difficult to make, because you have to be an experimentalist who makes the lens with the perfection required. And that's extremely hard, because if you want to do it at optical wavelengths, you're doing really nano engineering and have to work with very flat surfaces. So there has been some progress there. But what we've set ourselves is a simpler problem. So what a lens does is take every point in the object and it reproduces it as a point in the image, so point for point. We are working with things called harvesters, and what they do is they just take all the light that's incident on them and focus it down to a single point wherever the light comes from. So you can see it's a simpler function, but it retains the same challenge of making that point to which you draw the light as small as possible. Now, if you just use ordinary lenses, obviously that point can't be smaller than something like the wavelength of light, which is order of magnitude a micron. But what we're doing is using transformation optics to take devices which, so what we look at is the sort of mother structure, if you like, is a silver or gold waveguide. So you have two blocks of gold, and between them there's a space which acts as a waveguide. And if you have an atom which emits any light there, the light is just taken to infinity. It's harvested to infinity, which is a fairly useless thing. But you can make a coordinate transformation, a conformal transformation actually, of an inversion about the origin, which you choose to be at the atom which is exciting. And then, of course, points at infinity go to the origin, and your atom goes to infinity. So what you're dealing with then in the transform system, which you know all about because you solved the waveguide, right, is a system which starts with an atom at infinity radiating energy, captures that radiation, and instead of sending it to the origin, sends the infinity, sends it to the origin, which is a system of two kissing cylinders, actually. And the light is harvested to that point where they kiss. And the limitation there, as always, is with loss, but you can actually cram light into about 10 square nanometers if you replace the cylinders with spheres. And that's a factor of 10,000 compression over what you can do with a lens. So all sorts of things become possible then with nonlinear effects, giant Raman resonances, because you have a very intense concentration. One of the hassles in spectroscopy is that light tends to come no smaller than a micron, but the molecules you want to sense are of the order of a nanometer, or maybe a little more, but not much. And so the conversation is not a very fluent or happy one. But if you could squash the light down to the same size of the molecule, to 10 nanometers, then you're into the possibility of single molecule sensing, and people are beginning to do that. And that's a much easier experimental challenge than is making the whole thing of a perfect lens. So we're aiming for the practicalities, and people are already realizing these systems you can actually make. Debbie Smith has done experiments with spheres at a controlled distance from a flat gold surface, which is also another system you can get. And we hope that biosensing will be, single molecule biosensing will be one of the early applications that we make there, but also in the future nonlinear effects. But that's what we're doing.